Imagine you walk into a room where people are slowly moving around. No music, no rules posted on the wall. And yet something odd is happening. Some people drift toward each other without effort. They don't decide to. They just end up closer. Others do the opposite. They lean away. They keep distance. If they get too close, they push back. Here's the strange part. You can't tell who will move which way just by looking. Everyone looks normal. There are no labels, no signs, and yet the motion is real. That kind of invisible sorting happens everywhere in nature. Inside every piece of matter, there are tiny building blocks called atoms. And inside atoms are even smaller pieces. Two of them matter most here. One is called an electron. The other is called a proton. Each one carries a property we call electric charge. Protons carry positive charge. Electrons carry negative charge. When a positive and a negative get close, they pull toward each other. When two positives meet or two negatives meet, they push apart. That much we can measure very precisely. What charge is, at a deeper level, is still an open question. Physics can tell you how it behaves. It cannot yet tell you why nature chose this rule instead of another. Now let's talk about motion. Picture a large public square. People gather in small groups. Most stay close to where they arrived, but a few move freely. They walk through the crowd. They pass from group to group. Nothing is stopping them. Now picture the same square, but everyone is seated and strapped in place. They can look around. They can feel forces around them, but they cannot move. This difference matters. In some materials, like copper, many electrons are free to move. They are not locked to one spot. They can slide past atoms and drift across long distances. That freedom is what makes copper useful for carrying electricity. In other materials, like rubber, electrons are held tightly. They remain attached to their atoms. They can shift slightly, but they cannot travel. That lack of freedom makes rubber an insulator. When you place copper inside rubber, you are combining these two behaviors. Motion is allowed in the center. Motion is blocked at the edges. Electricity can flow where it is useful and stay contained where it would be dangerous. That is not an accident. That is design. Now let's slow down and talk about heat. Put a hot cup of coffee on a table. Wait a few minutes. The coffee cools. The cup warms. Nothing visible moves, but something is happening. Inside the coffee, atoms are in constant motion. When the coffee is hot, that motion is fast. The atoms collide often. They shake. When they hit atoms in the cup, some of that motion is shared. The coffee loses energy. The cup gains it. Heat is not a substance. It is motion at a small scale. Fast motion feels hot. Slow motion feels cold. When two objects touch, motion spreads from where it is faster to where it is slower. That is all heat transfer is. The same idea appears again when electricity flows. As electrons move through a metal, they do not glide smoothly. They collide, they scatter. Each collision transfers a bit of energy to the atoms of the wire. Those atoms vibrate more. The wire warms. That warmth is not a side effect. It is a direct result of motion and collisions. Electricity does not just pass through matter. It interacts with it constantly at every step. Now let's slow things down and look at how a push actually spreads. Imagine a long line of people standing shoulder to shoulder. No one is moving. Everyone is already packed in place. Now the person at one end takes a small step forward. They barely move, but the pressure they create is passed along the line. Almost instantly, the person at the other end feels it. Nothing traveled the full distance. The effect did. This is an important idea. Inside a metal wire, electrons are already there. They fill the wire completely. They are close together. Most of the time, they are just drifting slowly, not racing anywhere. When nothing is happening, everything is calm. Now apply an electric push at one end. Electrons near that end feel a force. They shift slightly. That shift presses on nearby electrons. Those press on the next ones. The influence spreads through the wire very fast, much faster than any single electron moves. The motion is slow. The message is fast. This is why a light turns on almost instantly when you flip a switch, even though electrons themselves creep along at a gentle pace. But there is a rule that cannot be broken. For electrons to keep moving, there must be a full path. They must be able to go somewhere and come back from somewhere else. If the path is broken, motion stops. When there is a gap, electrons pile up, forces balance, the system settles down, nothing flows. This is what a circuit really is. It is not a device, it is not a machine, it is simply a complete loop. Close the loop and motion can continue. Open it and everything freezes. Now comes something that sounds unsettling. The force that moves electric charges is incredibly strong. On the scale of tiny particles, it overwhelms gravity completely. If electric forces did not cancel so well, the world would not look anything like it does. And yet, you do not feel this force as you move through the world. You are made of charged particles. So is the floor. So is the air. Still, you walk calmly. Nothing explodes. Nothing flies apart. That is because nature keeps charge balanced with extreme care. Positive and negative charges almost perfectly cancel each other in ordinary matter. The pushes and pulls neutralize. What remains is a faint leftover force that we call gravity. This balance hides electricity from view. For most of history, people only noticed rare hints of it. Certain stones, certain materials, small effects that seemed unrelated. The deeper pattern stayed invisible because it was too well controlled. But that hidden balance is doing all the work. Every chemical reaction depends on it. Every molecule depends on it. The way atoms stick together, the way materials change, the way energy moves through living cells, all of it relies on electric forces between electrons and atoms. Electricity is not something added to nature later. It is already woven into matter itself. So now we are ready for the next step. Electrons can move, paths can be complete, forces can exist, but motion does not begin on its own. Something must tilt the balance. Something must create a difference. That difference is what we call the push, and that is where we go next. Now we can talk about the push itself. Imagine a long hallway with a smooth floor. You place a ball on the ground. If the floor is perfectly flat, the ball stays where it is. Nothing happens. There is no reason for it to move. Now tilt the floor just a little. The ball starts to roll. Tilt it more, and the ball rolls faster. The motion does not come from the ball. It comes from the difference in height. Electricity works in a similar way. Electrons do not move just because they exist. They move when there is a difference that pushes them. In electricity, that difference is called voltage. Voltage is not motion. It is a condition. It tells electrons which way is downhill. A battery creates this condition. So does a power plant. One side is made rich in electrons. The other side is made poor in electrons. When a complete path exists, electrons drift from one side to the other, responding to that imbalance. But not all paths are equal. Some materials make this motion easy. Others resist it. This resistance is not mysterious. It comes from obstacles at very small scales. As electrons move, they collide with atoms. They scatter. They lose energy in tiny amounts. A narrow wire offers fewer paths. A longer wire offers more chances for collisions. Both increase resistance. The electrons still move, but they are slowed and disturbed along the way. Those disturbances matter. Each collision transfers energy to the atoms of the material. The atoms vibrate more. The material warms. Resistance turns electrical motion into heat. This is not a flaw. Sometimes it is the goal. Inside a light bulb, the wire is designed to resist motion strongly. As electricity flows, the wire becomes extremely hot, so hot that it glows. Light is not the purpose of the wire. Heat is. Light is what heat looks like at very high temperatures. Now consider what happens when resistance suddenly disappears. If electricity finds a path with almost no opposition, it rushes through. The current becomes large. The wires heat quickly. If nothing stops the flow, damage follows. This is why electrical systems include protection. Fuses and circuit breakers exist to interrupt the path when current becomes dangerous. They are not smart devices. They simply react to excess motion and heat. Now let's talk about your body. Your body contains water. That water contains dissolved salts. This makes your body able to conduct electricity, not as well as metal, but well enough to matter. If you touch a source of high voltage while also connected to the ground, your body can become part of the path. Current flows through muscles. Muscles respond by contracting. That sudden contraction is what you feel as a shock. If the current is large enough or passes through the wrong regions, it can interfere with the signals that keep your heart beating. That is why insulation and grounding are taken so seriously. So here is the pattern. Voltage creates a push. Resistance pushes back. Current is what happens in between. This balance determines everything practical about electricity. And now we reach something unexpected. When electric charges move, they do not act alone. Their motion affects the space around them. Something new appears. When current flows through a wire, a magnetic effect forms around it. You cannot see it, but you can detect it. A nearby compass will respond. The needle turns. Motion in the wire has changed the space nearby. If you bend the wire into a loop, the effect grows stronger. If you stack many loops together, it grows stronger still. Place iron at the center, and the effect becomes focused and powerful. You now have a magnet that exists only while electricity flows. But this connection goes both ways. If you move a magnet near a wire, electrons inside the wire begin to move. No battery is required. Motion alone is enough. Changing magnetism creates electric motion. This is not a coincidence. It is a rule of nature. In power stations, large magnets are rotated near coils of wire. The motion of the magnets produces a steady electric push. That push travels through wires across long distances. The energy does not ride on the electrons. The electrons barely drift. What moves is the pattern, and that pattern is what we call electricity. Pause for a moment and follow the path of energy. Far away from your home, water flows downhill. That moving water turns large blades. Those blades rotate heavy machinery. Inside that machinery, magnets move past coils of wire. That motion creates an electric push, travels through long wires stretched across land and cities. When it reaches your home, it nudges electrons inside a thin filament or a small circuit. Those electrons collide with atoms. The atoms vibrate harder. Light appears. The river never goes near your lamp. The magnets never leave the power station. Yet the effect reaches you. Energy moves without anything physical making the journey. What travels is a pattern, carried by electric and magnetic effects working together. If you reverse the process, you get motion again. Send electricity into a coil placed near a magnet, and the coil begins to turn. The current creates magnetic effects. Those effects pull and push on the coil. Rotation follows. This is how electric motors work. Fans, pumps, elevators, and factory machines all rely on this same exchange. Electricity creates motion. Motion creates electricity. The roles can swap, but the connection remains. This deep link between electricity and magnetism was not obvious at first. It took careful thinking to uncover it. In the 19th century, physicists found that electric and magnetic effects could not be separated. When the mathematics was written carefully, it revealed something surprising. A changing electric effect creates a magnetic effect. A changing magnetic effect creates an electric one. Together, they form a self-moving disturbance that can travel through empty space. Even more surprising, The math predicted a speed. When that speed was calculated, it matched the known speed of light. This was not a guess, it was a consequence of the equations. Light, it turned out, is not something separate. It is an electromagnetic disturbance moving through space. When you see a flame, a screen, or a page of text, electromagnetic waves are entering your eyes. They are made of electric and magnetic effects changing together, moving outward at a fixed speed. Radio waves, visible light, and X-rays differ only in how fast these changes occur. The underlying process is the same. Now consider something much closer to home. You spend your entire life touching things, tables, floors, tools, other people. It feels direct and obvious, but at the smaller scales, that is not what is happening. When your hand presses against a table, the atoms in your skin approach the atoms in the wood. Their electrons come close. Those electrons carry the same type of charge. They repel each other. That repulsion grows very strong over very short distances. It stops further approach. The atoms never merge. They never overlap. What you feel as solid contact is an electrical response that resists compression. Touch is not contact between objects. It is a force acting across a tiny gap. This is why matter feels firm instead of ghost-like. Floors hold you up not because atoms are rigid blocks, but because electrical forces push back when you try to press atoms closer together. The response is fast. The forces are strong. To your senses, the surface feels solid. Now shift scale again, this time inward. Inside atomic nuclei, protons sit extremely close together. They all carry positive charge. By ordinary electrical rules, they should repel violently. Something else holds them in place. That something is called the nuclear force. It is very strong, but it acts only across tiny distances. In heavy nuclei, this balance is delicate. Many protons are packed into a small region. The electrical repulsion is always present, waiting. When a nucleus splits, the short-range nuclear force no longer holds the pieces together. The electrical repulsion remains. The fragments fly apart because like charges repel. The energy released in such events comes from changes in how forces are balanced inside the nucleus. Electrical repulsion plays a central role in driving the fragments away once the binding is broken. The result is a large release of energy in a very short time. So once again, the same interaction appears. Attraction and repulsion between charges shape events across enormous ranges of size. They help atoms bond, they help materials resist pressure, they help release vast amounts of energy under extreme conditions. Electric forces are everywhere, doing quiet work most of the time. They rarely draw attention because they cancel so well in ordinary matter. When that balance is disturbed, their influence becomes impossible to ignore. And yet most days they remain invisible, steady and precise, holding the world together without announcing themselves. Look up at a power line sometime. You may see birds resting on it, calm and unharmed. This feels strange at first. That wire carries a large amount of electricity. Why does nothing happen to them? The reason is simple. Electricity only flows when there is a difference that drives it. The bird touches the wire with both feet at nearly the same point. Both feet are at the same electrical level. There is no reason for current to pass through the bird. The electricity stays in the wire because that path is easier. If the situation changes, the outcome changes. If an animal or a person touches two wires at once, or touches a wire and the ground at the same time, the balance is broken. Now there is a difference. Now there is a path. Current flows. That is why people who work around power lines are careful with every movement they make. Water makes this danger worse. Your body can already conduct electricity. It contains water and dissolved salts. When your skin is dry, it offers some resistance. When you are wet or standing in water, that resistance drops sharply. Electricity looks for the easiest path. Wet conditions can turn your body into that path. This is why electrical systems are designed with grounding. Grounding gives electricity a safe route. Metal rods connect the system to the earth itself. If something goes wrong, excess electricity flows into the ground instead of through a person. The earth can absorb large amounts of charge without changing in any noticeable way. Lightning is nature doing the same thing on a much larger scale. Inside storm clouds, electric charge builds up. Different regions of the cloud carry different charge. The ground below responds. The electrical difference grows stronger. Eventually, the air can no longer resist. For a brief moment, it becomes a conductor. Charge rushes downward in a violent discharge. Lightning often strikes tall objects because the distance to the cloud is shorter. The path is easier to complete. Now step back from danger and look at history. Long before power grids and generators, a simple discovery changed everything. It was found that moving a magnet near a wire causes electric motion in the wire. No battery is needed, motion alone is enough. This insight made continuous electricity possible. Today, the same idea runs the world. Flowing water, moving steam, or turning wind spins large machines. Magnets move near coils. Electric pushes are created and sent outward through networks of wire. Energy from far away becomes light, heat, and motion where you are. That discovery did not explain electricity. It showed how to use it. And that brings us to an honest ending. We understand electricity well enough to predict it. We can calculate how it moves. We can shape it, guide it, and depend on it. Entire technologies are built on this knowledge. But the deeper question remains. What is charge, really? Why does it exist at all? Why do positive and negative behave the way they do? Physics does not yet have answers to those questions. It describes patterns. It does not explain their origin. That is not a failure. It is the nature of science. Long ago, people noticed small electrical effects and thought they were curiosities. Today, we know those same effects hold atoms together, drive chemical reactions, and make life possible. Still, the foundation remains partly mysterious, and that is something worth appreciating. The universe does not owe us simple explanations, yet it allows us to discover how it behaves. Little by little, we learn its rules. We test them. We use them. We build with them. Electricity is one of those rules made visible. We can work with it. We can trust it. We can depend on it. And the fact that there is still more to understand is not frustrating, and it is an invitation. So when you look back at everything we've traced, something subtle stands out. Electricity never needed drama to matter. It was always there. Long before wires, long before machines, long before anyone knew its name. It shaped atoms. It guided chemistry. It made matter hold together and energy move from place to place. We noticed it late, not because it was weak, but because it was balanced so well. That balance hides enormous strength. What we call electricity is not a single thing. It is a pattern of behavior. Charges attract and repel. Motion spreads through matter. Energy moves without objects traveling the distance. These ideas sound abstract at first, but once you see them, they start appearing everywhere. In heat, in light, in motion, in life itself. What makes this story remarkable is not that electricity is mysterious. It is that it is predictable. We can calculate what will happen before it happens. We can design systems that work every time. We can send energy across continents. We can turn motion into light and light into information. All of that comes from learning how nature behaves, not from guessing what it means. And yet, at the deepest level, a question remains open. Why does charge exist at all? Why do positive and negative behave this way and not some other way? Physics does not yet answer that. It may never answer it in the way we expect, but that is not a weakness of science. It is a boundary that keeps discovery alive. Understanding does not require final answers. It requires honesty about what we know and what we do not. What we know is enough to build. What we do not know is enough to keep us curious. Electricity is a perfect example of this balance. It is familiar and strange at the same time, ordinary and profound. It powers the devices around you, but it also explains why matter feels solid and why light reaches your eyes. It connects the smallest scales to the largest ones without asking for permission. There is no hidden message here, no secret meaning to uncover, just a quiet truth. Nature behaves in consistent ways. We learn those ways slowly. We test them. We rely on them. And sometimes, if we look closely, we realize that something we thought was simple has been quietly holding the world together all along. Electricity does not need mystery to be impressive. It is impressive because it works, and the fact that there is still more to understand means the story is not finished. It never is.